This video is the first 28 slides of Chapter 3, an introduction to organic compounds, nomenclature, physical properties, and structure. These first 28 slides will discuss how we name both linear and branched alkanes. So in review, hydrocarbons are molecules that contain atoms of dihydrogen and carbon. An alkane is a hydrocarbon that only contains single bonds, so sp3 hybridized carbon atoms. These alkanes are found from everything from natural gas to petroleum and are used all the time in chemistry. They have a generalized formula. For every carbon atom in an alkane, there are 2N plus 2 hydrogens. So let's take a look at that. If I look at methane, I have 1 carbon, so N equals 1, so 2 times 1 plus 2 equals 4, and indeed I see 4 carbons. If I go down here to butane, I see that there are 4 carbons, so 2 times 4 is 8, plus 2 is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, and that always works out for both straight chain and branch chain hydrocarbons. If we look at this series, I go from 1 carbon alkane, it's called methane, 2 carbon ethane, 3 carbons propane, 4 carbons butane, and 5 carbons pentane. These are all linear, they're all saturated, meaning they have as many bonds as they can take that are all single, and they're sp3 hybridized. They're made up of a series of what we call methylene groups, this CH2 groups. So if I look over here at pentane, you can see there are 5 CH2 groups that make up pentane. An unusual thing about this is that these are not alkenes. This is old terminology. So the ene here does not mean that this is a double bond. It's just old terminology related to spectroscopy and some solvation effects. Let's look at a longer list of linear chain or straight chain alkanes. Sometimes we call these N-alkanes. That's just terminology meaning that they're all in a straight chain. There's no branching. 1 carbon is methane, 2 carbons ethane, 3 carbons propane, 4 carbons butane. Those first 4 are historical names, and they are considered systematic names also. From there on end, we take the Greek or the Latin word that tells us how many carbons they are in there. So for example, if I have 5 carbons, pentane, 6 carbons hexane, 7 carbons heptane, 8 carbons octane, 9 carbons nonane, 10 carbons decane. I expect you to know those first 10. Okay? And then there's another series, and it keeps on going. Undecane, dodecane, tridecane, tetradecane, pentadecane, hexadecane, heptadecane, octadecane, nonadecane. And then when I get to 20, it's icosane. And then when I get to 30, it's triacantane. Okay? If I look at the boiling point, some physical properties of there, I can see quickly that it tends to go up as I get more and more carbons. And that's because there are more London dispersion forces between molecules. And if I have more forces, I need more energy is required to break them up to boil them. If I look at melting point, for linear chain alkanes, that trend is very similar. As I go to more and more carbons in my molecule, my melting point goes up. That's because I do have more London dispersion forces now between molecules, but I also have packing forces. And these packing forces and London dispersion forces, as they increase, I need more energy is required to melt the solid. If I look at the trend in density, notice there is a slight trend here, but the bottom line is that it is less than 1. 1 is the density of water. All of these molecules are less dense than water, and so they would float on top of water if they're immiscible. So these are some trends you should know. And looking again at these are my methylene groups. There's a term that our books uses that says that each of these just has a different number of methylene groups. Those are all called homologs of each other. Let's look at some constitutional isomers of alkanes. If I look at butanes, butanes are just hydrocarbons that contain 4 carbon atoms and 10 hydrogen atoms. There is butane, which is in a straight chain or linear chain form. Sometimes we call this N-butane. But I also could draw another molecule that has the exact same molecular formula, meaning I have 4 carbons and 10 hydrogens. In this case, I'm sort of looked at this branch-like structure here. Okay? This has a common name of isobutane. So there are 2 different butanes that I could draw with the same molecular formula. Those 2 are constitutional isomers of each other. Same molecular formula, just connected differently. If I look at 5 carbon systems or pentanes, I can draw 3 different pentanes. I could draw the linear chain pentane, N-pentane. I could draw isopentane. Notice it has these 3 carbons right here. That's sort of the iso group. This one has, let's see, I got 5 carbons there. I got 12 hydrogens. That has the exact same molecular formula as this N-pentane. And I can also draw a molecule called Neopentane. Both isopentane and neopentane are common names for these molecules. If I look a little bit, I can see that I could look at these in a different way. I could look at this chain right here and call that, well, that would be 4 carbons. That would be a butane. And I'd have this CH3 group sort of hanging off of it. We call this CH3 group a substituent. If I look at this molecule, I can see a long carbon chain here of 3 carbons. That would be a propane. And it would have 2 CH3 groups sticking off of it. Those would be substituents on a propane molecule. So substituents on our longest continuous carbon chain. So my longest carbon chain, as we often call, is the parent chain. That CH3 group that we talked about on the last slide, we call that a methyl group or a methyl substituent. And this squiggly line here, that represents my parent chain. So this squiggly line, there's some long continuous carbon chain that has more than 1 carbon on it. If I have a substituent that has 2 carbons on it, I call that an ethyl group. If I have a substituent that has 3 carbons on it, I call it a propyl group. Notice these terms right here sort of follow methane, ethane, propane, but instead of having ANE on it, I substituted the ANE for a YL. If there's a YL in a name, that means it's a substituent. If I have the isopropyl group here, 3 carbons branched right at this first carbon here, I could also have 4 carbon substituent, call that butyl. 4 carbon substituent that's branched at the second carbon here, isobutyl. I also could have a branched butyl that is slightly different. Instead of branching at the second carbon away from the parent chain, I branch at the first carbon. This is called isobutyl. This one is sec-butyl. Notice there's a hyphen in here. That is the correct way of writing it. You need to have the hyphen. I could also draw a butyl substituent with 4 carbons in it that has 2 methyl groups at that first carbon attached to my parent chain. We call this tert-butyl, or in sort of abbreviated form, T-butyl group. You need to know these common groups, and we will talk about these an awful lot throughout the semester. Let's now look at 6 carbon constitutional isomers. In this case, I have 5 ways of drawing them. If I draw the linear chain, I'm going to call that N-hexane. In this case, this does have a common name to it. I could call this isohexane. Notice that I have this 3 carbons here at the end here. That sort of looks like isopropyl and isobutyl. Officially, we're going to call this 2-methylpentane using the Iupac system, which we're going to discuss in a few slides. I just want to introduce some of the Iupac system. This one is called 2-methylpentane. That's because my longest continuous carbon chain is 5 carbons, pentane, and I have a substituent, which is a methyl group. Here my longest continuous carbon chain is 4 carbons long, so we're going to call this a butane with 2 methyl substituents off of it, starting at the 1 second carbon over. So I'm going to call this 2,2-dimethylbutane. In this molecule, my longest continuous carbon chain is 1, 2, 3, 4, 5 carbons long, and I have a substituent, a methyl group again, off carbon number 3, so I call this one 3-methylpentane. Here I have 1, 2, 3, 4 carbons that are my longest continuous carbon chain, or my parent chain. So this is going to be a butane with 2 methyl groups off of it. So I call this 2,3-dimethylbutane. This is carbon number 1 of my parent chain, carbon number 2 of my parent chain, carbon number 3 of my parent chain, carbon number 4 of my parent chain. If I have a hydrocarbon with 7 carbons in it, notice I'm still going to have my 2n plus 2 formula here. 2 times 7 is 14 plus 2 is 16, so I know it is a saturated hydrocarbon. I could have the linear version N-heptane. I could have the isoheptane. I could also call this 2-methylhexane because I have 1, 2, 4, 5, 6 carbons in my longest continuous carbon chain, and off carbon number 2 I have a methyl group. I could have my methyl group off carbon number 3. We'd call it 3-methylhexane. I could also have arranged these carbon atoms 1, 2, 3, 4, 5. So my longest continuous carbon chain in this molecule is 5. And I have 2 methyl substituents. I have a 2,3-dimethylpentane. Here is also a pentane, but in this case I have the substituents at carbons number 2 and 4. Here is my another pentane with an ethyl substituent off it now, so I've rearranged it. So 1, 2, 3, 4, 5 is my longest continuous carbon chain, and I have a CH2CH3 substituent. I also could have 2 substituents off the same carbon. This would be 2,2-dimethylpentane. Here is 3,3-dimethylpentane, and here is 2,2,3-trimethylbutane. 1, 2, 3, 4, my longest continuous carbon chain. In other words, there are 9 different ways I could arrange the skeletal structure of C7H16. Those are all constitutional isomers of each other. If I have 10 carbons, there's actually 75 different constitutional isomers I could draw. If I had 15 carbons, there's 4,347 different alkanes that I could draw, or constitutional isomers. Now let's talk about the nomenclature the systematic way, looking at some common names and comparing them to the Iupac names, the International Union of Pure and Applied Chemistry. To make it a little bit harder, there is, in the 1970s, they came up with a methodology for naming organic molecules. We'll call that the old Iupac method. And then in the 1990s, they revised that to change it a little bit. So we have to learn common names and 2 different Iupac methodologies now. Iupac stands again for International Union of Pure and Applied Chemistry. It's the systematic method for naming molecules. It also retains some of the common names like methane, ethane, propane, butane, and also these iso, neo, sec, and tert prefixes for some molecules because they were named so long ago and they are common. They had to include them in this Iupac system. So for larger alkanes, we're going to have the suffix "ane" at the end of every one of our names, and then we're going to have a prefix that represents the number of carbons. So after I get above 4, I'm going to start using pent, hex, hept, things like that. So if I look at a 5-carbon system as an example, I'm going to call this pentane. Let's now methodically go through the official rules for naming hydrocarbons. I first want to find my longest continuous carbon chain, and that is going to become my parent chain. So in this first molecule, I count 1, 2, 3, 4, 5 is highlighted in pink here. There's 5 carbons, so this is going to be a pentane. If I look at this second molecule down here, notice I didn't go linearly across the page horizontally. I actually started way down here and called that 1, 2, 3, 4, 5, 6 instead of 1, 2, 3, 4, 5 or 1, 2, 3, 4. I wanted to find my longest continuous carbon chain, and that's 6 carbons. So this molecule's parent chain name is going to be hexane. I next need to number those carbons, and I want to number that parent chain in a way such that I give the lowest possible number to any substituents. For example, if I named this carbon here 1, 2, 3, 4, I hit my substituent at carbon number 4. But if I started at the right-hand side, I'd go 1, 2. I hit my substituent. So the correct methodology is to start numbering from right to left in this molecule. In our second example, if I started 1, 2, 3, 4, I'd get to my substituent if I started from the right-hand side. But if I start down here at the bottom left, I go 1, 2, 3. I hit my substituent at carbon number 3. So I'm going to start to the left bottom in this case, numbering my parent chain carbon atoms. So if I have one substituent, I want to name it, and then I want to locate it on my parent chain by number, remembering that separating numbers and letters by hyphens. So if I go 1, 2, I got a 2-methylpentane. And remember, I have a hyphen there. If I look at my second example here, I go up 1, 2, 3. So I'm going to have a methyl group at carbon number 3. So I have a 3-methylhexane here. If I have 2 or more of the same substituent, I do want to name them as a group. So if I have 2 similar substituents, I call it di. If I have 3, I call it tri, 4 tetra, 5 penta, etc. I want to number specifically at each location, separating my numbers from each other by commas. So for example, on this molecule, my parent chain has 5 carbons, so it's a pentane. I have a methyl group at carbon number 2, and I have a methyl group at carbon number 3. 2 substituents, both are methyl, so I'm going to call it dimethyl. And then I just put the numbers out in front. So I have a 2, 4 dimethylpentane. In the second example down here, I have my parent chain has 5 carbons again. I have 2 methyl substituents. Both of them are at carbon number 3 on my parent chain, so I call this 3,3-dimethylpentane. If I have substituents more than one that are different, I need to number and name them separately. Again, putting the number in the direction that gives them the lowest number. So if I look at this molecule, my parent chain has 5 carbons, so it's going to be a pentane. I have a methyl group here at carbon number 2, and I have an ethyl group here at carbon number 3. So I need to put that all together. I always want to list my substituents in alphabetical order, not based on the numbering system. So in this case, I put ethyl first because E comes before M. So this is still 3-ethyl, 2-methylpentane. Notice I still have a hyphen between each number and letter. Hyphen and a second hyphen over here. Notice that when I'm doing alphabetation, I do not include di, tri, tetra, or penta. And I'm going to have several examples of that coming up. So let's look at these examples here. What if I have more than one possibility for this lowest number? So if I look at this molecule, I have 1, 2, 3, 4, 5. The parent compound is going to be pentane. I have a 1, 2 dimethyl and a 4-methyl. So that's going to be a trimethyl. So I'm going to go 2, 2, 4 trimethylpentane. If I had started over here on the right-hand side, I still would have got to the substituent on carbon number 2, but then I would have had a higher numbering system over here. I would have had 2, 4. So we don't call this 2, 4, 4 trimethylpentane. We start over on the left-hand side, so I get a lower overall numbering system. Another example here is that I go 1, 2, 3, 4, 5, 6, 7, 8. I have 8 carbons in my parent chain. That's going to be an octane. I have a substituent at carbon number 3 if I started on the left-hand side. I have a substituent at carbon number 3 if I started numbering on my right-hand side. So I need to look at other substituents to get a lowest number. And sure enough, this other methyl group here is closer to the left-hand side. So in this case, I'm going to go 1, 2, 3, 4, 5, 6 ethyl. And then I'm going to have a 3, 4 dimethyl octane, because I get a lower numbering system if I start from the left rather than starting from the right. So let's look at punctuation again and summarize that. I want to separate numbers from each other by commas. So for example, I have a 2,3-dimethyl in this name, a comma between them. I want to separate numbers from letters with hyphens. So everywhere I have a number next to a letter, I put a hyphen. So I have 4-ethyl, 2, 3, dimethyl, 5, propyl, nonane. Notice there is no punctuation between my very last substituent and my parent name. Let's make sure this name is right. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, so that's going to be a nonane. I have a methyl at carbons number 2 and 3, so that's my dimethyl. I have an ethyl at carbon number 4, and I have 3 carbons or a propyl at carbon number 5. I go E, M, and then P. Notice again, we do not include the D in my alphabetation system. Occasionally, I'm going to run into a longest chain that has equal length exists, and I'm going to use the chain with a greater number of substituents. For example, if I look at this first molecule over here, it's the same molecule both sides, but I've actually called this one 1, 2, this green here is my parent chain, 1, 2, 3, 4, 5, 6, 7. Or I could have gone in 1, 2, 3, 4, 5, 6, 7. In this case, I have 3 substituents, a methyl, and an isopropyl. If I look over at the second molecule, I have 4 substituents. This is the molecule that I'm going to use here to actually do my nomenclature. So this is correct. I have 7 carbon chain with 4 substituents. Okay. Now let's number this carbon chain. Let's see, if I start from the top, I go 1, 2, 3, I hit a substituent. If I started from the bottom, I get 1, 2, I hit a substituent. So in this case, I want to actually start at the bottom here because I hit a substituent earlier. So in this molecule, I'm going to now name that. Let's put all those rules together and name this molecule. So first, I want to name all the groups attached to my parent chain. Let's see, I have a methyl group at carbon number 2. I have an ethyl at carbon number 3. I have a second methyl group at carbon number 4. And I have a third methyl group at carbon number 5. I can then condense that into 3-ethyl, 2, 4, 5 trimethyl. My parent chain is still 7 carbons, so that's going to be a heptane. Putting it all together, 3-ethyl, 2, 4, 5 trimethyl heptane. Again, noticing that E comes before M in this molecule. Let's do some examples here. Let's see. I'm going to look for my longest continuous carbon chain. 1, 2, 3, 4, 5, 6. This is going to be a hexane. This is going to be a 3, 4 dimethylhexane. I could have redrawn that. If I look at this molecule, and I can sort of quickly see that it's 1, 2, 3, 4, 5, 6, 7, 8. This is going to be an octane. This is going to be a 3, 6 dimethyl octane. If I look at this molecule, 1, 2, 3, 4, 5, 6, 7, 8. This is also an octane. This is going to be a 3, 4, 4, 5 tetramethyl octane. So how about Iupac names for those small molecules that we talked about before? If I have butane or M-butane, those are both Iupac names. Isobutane is an approved Iupac name, but I also can name that systematically. Okay, so I can name this as 1, 2, 3 carbons. I can name this as a 2-methylpropane. If I look down here at my pentanes, 5 linear carbons, that's just going to be pentane or N-pentane. This would be the common name, and the approved Iupac name would be Isopentane, but the systematic Iupac name would be, let's say, 2-methylbutane. Here I would have Neopentane as my common and my approved Iupac name, but I could also do it systematically by looking at these two as substituents. So I have 3 carbons as my longest continuous carbon chain, and I have 2 methyls coming off that second carbon, so this would be 2,2-dimethylpropane. What if I have a very complex substituent? So here's a molecule where I've drawn this parent chain as a squiggly line. There are some rules to that, so I want to find the longest continuous carbon chain of my substituent, starting at the point that it's attached to my parent chain. So I'm always going to start up here. 1, 2, 3, 4, as shown in pink here. That's going to be a butyl group. And then I want to start numbering, and I always start numbering at that first carbon attached to my parent chain. So I always start here as 1. So if I count down here to 2, I notice that I have 2 methyl substituents on my substituent parent chain. So this is going to be a dimethyl groups here. Okay. If I put that all together, I then want to put that together and put parentheses around it. So my substituent now is called 2,2-dimethylbutyl. And that would be attached again in my name to my parent chain, whatever it is up here. Okay. So let's look at some alternative Iupac nomenclature for some branch chain molecules. Again, we have my methyl substituent, we have my ethyl substituent, propyl substituent, and my butyl substituent. We also can have a propyl substituent that is branched here, the isopropyl. We could call that carbon number 1, carbon number 2, so it's going to be an ethyl substituent with a methyl group off of it. So this is a 1-methyl ethyl substituent. If I look at my 4 carbon substituents, here is 4 carbons. I have a 1, 2. I have a methyl group at carbon number 2, 3 carbons total. So this is going to be a 2-methylpropyl. This is going to be a 1-methylpropyl. This is my longest continuous chain starting at carbon number 1 is in 2 carbons, so it's an ethyl. So this would be a 1,1-dimethyl ethyl group. Know these common and Iupac names, systematic and common. In this first substituent, I'm going to start naming these. We're going 1, 2, 3, so that's going to be a propyl. At carbon number 1, I have an ethyl. At carbon number 2, I have a methyl. So this is going to be a 1-ethyl, 2-methylpropyl. Why didn't I just go up here? 1, 2, 3 carbons. I get the same number of carbons, so this wouldn't have been a propyl, but I only have 1 substituent on my substituent. So this is the correct methodology for naming this molecule. If I look over this substituent, I go 1, 2, 3, 4 carbons, so that's going to be a butyl. This is going to be a 1, 1, 3 trimethylbutyl. If I look at this molecule now, it contains some very complex substituents. So let's look at this molecule. I got 1, 2, 3, 4, 5, 6, 7, 8, 9. This is going to be a nonane. I can sort of look at it quickly and see I should call this as carbon number 1. 1, 2, 3, I get to an ethyl group, and then I get to this more complex substituent, which is the one right up here. So putting that all together, I get a 3-ethyl, and then at carbon number 5, I have my substituent, my 1-ethyl, 2-methylpropyl group, and then my parent chain. Notice I have parentheses around my complex substituent, my parenthetical substituent. I still need to number that, and I still need to use my correct punctuation. Now let's actually draw some molecules based on their name. We're going to start off at the top here by looking at the parent chain here. That's got 9 carbons, so I'd go 1, 2, 3, 4, 5, 6, 7, 8, 9. Off carbon number 5, I have a sec-butyl group. 1, 2, 3, 4, 5. So I'm going to come down here. If I remember the sec-butyl, I actually have a branch coming off here. And then I have 2 more carbons coming off there. I could draw it a little bit nicer if I were to draw it like that. Okay. In this second molecule, I have my parent chain has 7 carbons. So 1, 2, 3, 4, 5, 6, 7. Off carbon number 4, I'm going to have a chloro group. 1, 2, 3, 4. So I could draw a chlorine up here. Off carbon number 2, I have a methyl group. And that's it. Okay. If I look at this fourth example here, again, I have 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Off carbon number 3, I have a methyl group. Off carbon number 4, I have a methyl group. Off carbon number 5, I have an isopropyl group. That's a 3-carbon system here. Okay. So that would be that molecule. On the fourth example here, I also have 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Off carbons number 3 and 4, I still have a methyl group. And off carbon number 5, I have a 1-methyl ethyl. So I draw my ethyl group, and I draw my methyl group off of there. In fact, it's the same molecule. That's 2 different ways to name the same molecule. This using the parenthetical name for my substituents. Let's name the following molecules. First, let's start off and let's actually find the parent chain. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's going to be a decane. I can look at this 1, 2, 3, 4 or 1, 2, 3, 4. I could start at either side here. So I'm actually, in this case, I'm going to start on the left-hand side because I get a lower number here for my more complex substituent. So that's going to be a 1, 2, 3, 4. I'm going to have an isopropyl. 6, 7. I'm going to have a methyl group here. Okay, so 4 isopropyl, 7 methyl decane. If I did the parenthetical nomenclature system for that, I have a 1-methyl ethyl. Notice here that when I do that, these two, I have different alphabetization. Here I have an I before an M. Here I have an M before a M-E. So in this case, when I do the alphabetation, I go M-E-T-H-Y-L. Here I go M-E-T-H-Y-L-E. This is higher in the alphabet, so it comes second. So whether you use the common substituent name or the parenthetical substituent name might affect how you put them together alphabetizing wise. If I look at this molecule and highlight the parent chain, 2, 3, 4, 5, 6, 7, 8, 9. This is going to be a nonane. If I start from the top here, I have a chloro at carbon number 3. I have a propyl at carbon number 5, and I have an ethyl at carbon number 6. Putting that all together, 3 chloro, 6 ethyl, 5 propyl. Notice I'm looking at the alphabet again, C, E, and P there. Now let's look at some more complicated molecules. If I look at this one and find my longest continuous carbon chain, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If I look at that, so that's going to be an undecane. If I look at it, I'm going to start numbering down here so I could hit this methyl substituent first. So 1, 2, 3 methyl, 4, 5, 6, 7 methyl. So I have a 3,7 dimethyl. On carbon number 6 here, I have my longest continuous carbon chain here is 3 carbons, and I have an ethyl group off of that, off of carbon number 1. Putting that all together, I get a 6,1-ethyl propyl and 3,7-dimethyl-undecane. If I look at this molecule down here and sort of find the longest continuous carbon chain, it takes a little bit of work here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's going to be a tetradecane. I'm going to start off here on the right-hand side because I hit a methyl substituent first. So here's methyl, here's an ethyl, here's a propyl with an ethyl group off of it. Here is a butyl with both an ethyl and 2 methyl groups. Here is another propyl with a methyl group. And finally, my last substituent is this ethyl. So I put that all together, and let's see if we can sort of rationalize all that. So I have 3,11-diethyl. So here's my 3. Here's my 11. Both of those are ethyls. On carbon number 7, I have a 1-ethyl. Let's see, carbon number 7. 1, 2, 3, 4, 5, 6, 7. I have a butyl group. Off of that, I have a 1-ethyl. And I have a 2, 3 dimethyl. That's my second substituent. Off carbon number 4, I have a propyl group. And off that propyl group, I have an ethyl group at carbon number 1. So 1-ethyl propyl. Off carbon number 2, I have a methyl group. So that would be this one right here. And finally, off carbon number 8, I have a propyl group again with a methyl group off of carbon number 1. So we call that a 1-methyl propyl tetradecane, putting that all together.